Hello, everyone. So, welcome to sort of last minute review kind of session ding. Um, I was meaning to post this sooner, but um, as you get older, you get increasingly more busy, especially when you enter your 30s. Yeah, just a lot more responsibilities to think about. But anyway, let's talk about the first midterm, some of the topics that are going to be on there, and I'm going to keep it kind of short, I hope. But it'll just be a summary of what topics you should know, and I'll go over a few concepts and things you should know. But this is not meant to be a comprehensive review. Students should be reviewing all their notes, all the discussion worksheets, all the extra worksheets or practice problems, especially in addition to the textbook. Okay, so let's begin here. All right. So some things we want to remember. So for some topics here. So here's midterm one topics. Okay. So number one. So I'll just base these based on chapter. I'm not sure what's chapter one and chapter two, but chapter one, comma, let's do comma two. Comma two. Okay, you should know acidity of atoms. So acidity of compounds. So which has the most acidic hydrogen. So acidity and basicity of functional groups. So what functional group or what so what functional group is the most acidic and which functional group is the most basic in the compound? And like which one of these, bases are the most basic? Okay? So acidity and basicity, you want to know about hybridization and orbitals. Of orbitals and bonds. Okay, so you want to know which bonds, what orbitals are composed of this bond. So that was a problem in the practice exam. So I would know how to do that for any compound we draw at you. Okay. You want to be able to draw Lewis structures. And resonance structures. You also want to be able to know so Lewis structures and resonance structures. You also be aware of molecular geometry. Okay, and drawing isomers. Okay. So I think that's pretty much chapter 1 too. Also drawing organic compounds. So you want to be able to draw a formula, write the formula, condensed formula, Kukui, and bond line. Alright, so that's chapter 1 and 2. Now let's go to chapter 3. So here's chapters 1 and 2. Now let's go to chapter 3. Chapter 3. So, big one is nomenclature of cyclic and acyclic alkanes / haloalkanes. Okay? And then you want to know about halogenation reactions. Halogenation reactions. Okay? So halogenation reactions involving F2, Cl2, and Br2, because those are the only ones that can do a halogenation reaction. So you want to be able to predict product, write the reaction mechanism, with curly arrows. So after this course, you will either love these curly arrows or you will despise them. Okay? So the mechanisms, from a lot of students that I've taught over the past, or have taught, helped teach with or for, honestly, the best way to understand mechanisms is not just look at it, but make flashcards or kind of memorize it. But not just memorizing it, but practicing doing the mechanism so you can kind of convince yourself, okay, this is the most reasonable process for this reaction based on what we know about, bond strengths, chemical reactivity. So we kind of have to take into account what we learn from general chemistry and apply it now to organic reactions. Okay, so now we're kind of applying it to, energies, energy of compounds, stability, and patterns of reactivity. So that's pretty much the best advice I can think I could give everyone about reaction mechanisms. Okay, so reaction mechanism with curly arrows, you want to be able to write it, and also calculate. You may be asked to calculate delta H of reaction. Okay? So you want to be able to predict the product based on selectivity. Okay? So that's chapter 3. I think that's all I want to mention about chapter 3. Yeah, and also, I almost forgot, Newman projections. Of both alkanes and cyclic alkanes. So we can also draw them for cyclic alkanes. So don't forget about that. Okay, chapter 4 now. All right, chapter 4. What should we talk about in chapter 4? Okay, so basically you want to know about drawing alkanes. So drawing cyclic alkanes. Okay, and you want to pay specific attention to cyclopropane, the triangle, cyclobutane. It looks like a square, but it's actually a rectangle. But that's not important. Cyclopentane. Then cyclohexane. Okay, so you want to be able to draw cyclic alkanes, and then you want to be able to draw chair structures, and most stable conformation. Most stable conformer. So most stable conformer with substituents on it. Okay. So you're going to have substitute cyclohexanes. And you might be asked, draw the most stable chair conformer. Okay. All right. So that's the chair structures. And then other than that, I think that's all you can expect for chapter 4. Drawing these cyclic alkanes, and then what's most important is the chair structure, because that's one of the most one of the most studied cyclic alkanes out there is the chair structure. So it's a very important structure, and it has a lot of implications in chemical reactivity, properties, and other stuff of interest, not only in organic chemistry, but in other aspects too, like biology. Biology, they're composed of like sugar molecules, and usually we draw sugars that look like this molecule. And you have OH bonds here, here, here. But don't worry, you don't have this won't be tested in here. All right. So molecules like this is known as glucose. So a very important molecule. So that's why we study the chair structure, because these molecules they actually have unique shapes and conformations in the body and in environments other than water, or other than just like organic solvents and stuff like that. Okay, so that's pretty much all we want to be able to do for this first midterm. One last thing I'll note is you want to also note the difference between conformers, like chair conformers, structural isomers, okay, and cis-trans isomers. Okay, so now enough of that. Let's get into the actual material now. Okay, so first let's go over a bit of, kind of concepts here. So let's draw a line under here. Let's write in blue. I'm feeling blue's my favorite color. All right. So when we draw two chair structures, okay? Okay, so say I have 1,2-dimethyl cyclohexane. I'm going to just draw the cis isomer, okay? All right. So I draw this. We know it's in equilibrium with my other chair structure. So my other chair structure is not, as you're not flipping the chair on itself, you're flipping two of the bonds that are bent in the structure. So right here and right here. So now if we flip these bent bonds here, we're going to swap them. One's going to point down, one's going to point up. We get this structure. Okay. Okay, so now the methyl at this position right here is going to be right here now, and the methyl at this position is actually going to be right. Let's see here. Where would that one go? Right. It'll be up. It'll be down here now, right here. Okay. So what happens is when we do a chair flip, what kind of happens is that the positions are kind of moving counterclockwise. If you kind of catch my drift here. So you see this position. Okay, so this position right here, it kind of moved to this position now, right? So it kind of moved one position down or forward in a counterclockwise fashion. And you see this position here, it went. This one is kind of strange, but this one went over here. Oops. Right. So it looks kind of strange. All right, but that's just something we kind of have to remember. I know it's not an ideal situation, but if we just think, you could kind of think of it like, let's see, what's a good way to think about this? Because I always tell students just memorize it, but it's kind of hard to visualize like that. So imagine you're taking this bond right here, and now this one is going to be pushed up, so it becomes right here, right? It becomes pushed up right here. That's how we can tell that this position is yeah, it becomes a little strange if we think about it. So just imagine that these chairs are really flexible. So what happens is that this position at the top there, what actually becomes what it's actually doing is that you're the one thing we can think about is that, so the thing is, we can't, a chair flip doesn't mean that you're actually flipping the chair. What you're actually flipping is like a set of bonds. So let me see if I can explain it in a way that actually makes sense. Okay. Okay. Oh, okay. So imagine, I know it's really hard to imagine this, but we really need a diagram. And unfortunately, right now, I don't have my model kit. So if students are confused about this, after this exam, they could come talk to me, and I'll show them with a chair structure. But what really happens is, okay. So what's happening is you're taking this bond here. So let's erase these arrows. Oops. What you're doing here is you're taking this bond here, and you're bending it. Okay? So you're kind of bending this bond, you're bending it downwards here. So this is downwards, and now this is going to bend upwards. So now that's why it looks like this picture here, these points here. And so when you do that, this position goes over here because you're kind of twisting, you're kind of taking the mirror image of it by bending one bond upward and one downward. So you get this picture on the right here. So this picture. So you bend that bond, you see here, this point comes up here, right here, and this point comes back down, and when we bend up there. So the thing is, when you twist the bonds here, when you go from one chair to the other, the axial bonds go to equatorial bonds, and the equatorial bonds go to the axial bonds, but stereo stays consistent, so it doesn't change. Okay. I think that's the best way to think about it. Okay. So now which one is the most stable? Which one will be the higher in energy? Okay. So the thing is, so if you think about the hydrogen atoms here, and here's CH3. So the CH3 is going to clash with a set of hydrogen atoms that are axial. So you have two set of hydrogen interactions here. So this is called 1,3 diaxial strain. And that's because the methyl group is a large molecule, or a large part of the molecule, and it can interact with the ring based on the clashing with the hydrogen atom. So it's kind of similar to torsional strain and steric hindrance. Okay. So we could say axial substituents. Okay. Around the chair. Chair cyclohexane are higher in energy. Due to diaxial interactions. Okay, so that's the primary reason why we draw a chair form that's more stable. Okay, so the precise name for this is 1,3 diaxial strains. Okay. So that's the thing about chairs. So this one would be the most unstable. Actually, no. They're actually pretty much the same stability, actually. Yeah, so these are both... So yeah, both of these are pretty much unstable because they're equivalent, right? Because they're the same methyl group. So if we made this one, let's see here. So if we made this a fluorine atom here. Okay, so if we made this a fluorine atom. Fluorine is smaller, right, than a methyl group. So it's not going to have the same kind of interactions as a methyl group. So this one would be more stable because fluorine is not as bulky as a methyl group. So this one would be the most stable chair. Of the compound, okay? So if you were to record a spectrum of this molecule at low temp, you would primarily see it in this form, right here. Okay, let's go on. So remember, for Newman projections, remember, the staggered form is always going to be the more stable form than eclipsed. Okay, so that's just something we should remember. So I'm not sure if you guys, if everyone learned this, but when we have conformers like this, we call them rotamers. So they're conformers of the same compound. Conformers. Another word for conformers. Okay, rotamers. Just another word for conformers. So you ever heard of that? Okay. Okay. All right. So, remember for our general reaction here, we'll say we have, CR4, where R equals alkyl group, or H. So for a reaction of R4 plus, halogen, let's say X2 is a halogen, X equals halogen. which is ClF4Br, we're going to have a situation where we get, well, R equals alkyl or H, right? So we should actually say, change this, sorry. Let's change this to, actually, it's okay. Let's keep it R4. Sorry about that. So, you know, as long as one of these R's is H, we'll get substitution, right? So we'll get CR3, and let's just say we get a BR here, or an X plus HX, right? Okay, so in these situations, when you have reactions that are selective for particular products, they tend to be slightly exothermic, right? So when you have selectivity, so if reaction is selective for a particular product, okay, it tends to be slightly exothermic. And the reason why it's just slightly exothermic is because there's competition, right? You're going to have processes that are going to be also competing for another product, and they can be similar in energy. So usually if things are selective, like chlorine, it's only going to be slightly exothermic. For prime example is chlorine for a secondary or tertiary carbon atom. So an example would be if you had this compound here, like this, there will be competition for this product and this product. Okay, so that's why when you have selectivity, there's going to be there's still going to be favorable processes, but the difference between one product versus the other is based on a very slight difference in their exothermic behavior. Okay, all right. So we're kind of covering all the bases here with this kind of vocab here. Okay. Now let's talk about something a little bit different. All right. So we have ring structures, right? Which one is the least, well, which one is the most stable? Okay, so remember if you try building models of these rings, you'll probably figure out that it's easier to make a 6-membered ring versus a 3-membered ring. So if you try to make a 3-membered ring, you're going to feel some resistance from the bonds, and that's because that resistance represents the amount of energy built up in the ring system, okay? So the stability here, so it's going to be more stable this way. And this is due to 2 factors. Reason 1, less ring strain. Okay? And ring strain is made of 2 components. Ring strain has both bond angle strain. So it's the strain. So this refers to this energy due to compressing bond angles in a ring. Okay, so that's due to the increase in energy due to compressing a bond angle in a ring. So in cyclohexane, it has the least amount of bond angle strain, but in cyclopropane, you see these angles here, they are 60 degrees, so that's very strained. In cyclobutane, they're 90 degrees. In cyclopentane, I think it's 105 or something. Let me see. No, it's not 105. I think it's 70. It's not 72 though. Let's see here. Yeah, I think it's a little bit like... No, it can't be. It can't be 72. I should know this. Okay, let's see here. Well, I don't think there's any bond angle strain in cyclopentane, but so... Let's see here. Oh, okay. Let's see. Yeah, they're not, that is interesting. Okay. Oh, wait. I think I know why. Okay. So we'll have to go back to a little bit of geometry here. So if you want to find the interior angles of any pentagon, remember it's n minus 2 times 180. Okay, so for 5, it's going to be 5 minus 2 times 180, which is 3 times 180, and that's 540. Okay, so each angle in the pentagon here is 108 degrees, so that's okay. And then if we do 6 now, so we get 4 times 180, it's 720. And 720 divided by 6 is about 120. Okay. All right. And so it's about 108 because it kind of adheres to the regular pentagon. And then for a cyclohexane, since the cyclohexane is so wiggly, these are at the perfect 109.5 degree angles right here. Okay, but don't pay too much attention to that. And you see here, remember for a tetrahedral bond, so all these centers are sp3 hybridized. sp3 hybridized wants angles around 110 degrees, right? So, or 109.5. Let's just make it specific here, 109.5. And that has been proven by experiment. Okay? So the more you deviate from these angles, the more bond angle strain you have. Okay? So this includes also additional strain. This is also called, we have torsional / eclipsing interactions or strain. Torsional / eclipsing strain. Okay, so just think, the ring structures, rings bring atoms closer together. So there's going to be more strain, right? There's going to be more eclipsing strain because the atoms are now approaching each other more closely. So that's just kind of a fact in all structures. So torsional eclipsing strain is usually not it's usually a medium or minor strain in the molecule. Usually the most strain comes from steric hindrance or, where large substituents are crashing within the molecule. And also when you constrain bonds and bond angle strain, that also causes these compounds to be unstable. Okay, so chair is pretty much our most stable compound. And then once you get to like higher ordered rings, like 7, 6, like 7, 8, 9, 10, you get other forms of strain, and that's called transannular strain. I'm not sure we talked about that yet, but when you get to higher ordered rings, you have what's called bigger ring sizes. You can get situations where now you have substituents across the ring interacting with each other, and this is slightly different from diaxial interactions, but it's kind of related. Okay, so 5 and 6 size rings are most stable. So that's why in most products, or most organic products, natural products, you see mostly 5 and 6 membered rings. But that's not always the case. You can have stable 9 membered rings, 7 membered rings, 8 membered rings. So there's a large variety out there. Okay. So the ring strain. So which one has the greatest ring strain? It's going to be rings with 3 atoms. Have the largest and then rings with 6 atoms have the least. Okay? Okay. All right. So that's how we determine the stability of our rings here. 3-membered ring triangles, they're very small, very compact, not very stable. Squares are not that much better. There's still a decrease in bond angle strain, but it's still very reactive. Cyclopentane's almost there. It still has some eclipsing interactions. And then the cyclohexane's the best because the chair structure has no eclipsing interactions and it's bond angle strain free. So it has the least amount of ring strain, which is close to 0. Okay, so that's the ring strain. All right. Okay. All right, so pi bonds. Okay, let's talk about pi. So let's just talk about resonance for a bit. So say I have this structure, right? Okay. So remember, alkenes or double bonds, they have sp2 orbitals, but they also have p orbitals. So the reason we could draw resonance structures between these two molecules right here and form this compound, okay, is because these all have p orbitals. So you see here p orbitals. So the p orbitals, they can interact right here. So when we do that, we can say, okay, all these double bonds, they kind of move along a train track, right? And so these p orbitals allow us to draw these double bonds like this, like moving it from here to go to here. It's because of these, it's kind of like, these p orbitals are stations for electrons. So they allow electrons to travel between each of these like kind of terminals, okay? So when we do that, the electrons can cycle back and forth, and then the structure and the integrity of the structure is maintained. Okay. So what can we say? About p orbitals then? So these are what we call p orbitals, right? Remember p orbitals? They are they exist above and below below the line of the atoms. So p orbitals. So what do p orbitals form? They form pi bonds. So sorry, I meant to say pi bonds. So they're pi bonds, right? And these pi bonds, they're above and below the line of the atoms and are formed and are made or formed made by overlap, made by side to side overlap of p orbitals. You see here that the overlap in this structure is due to the atoms in the same plane. So they're interacting because they're lined up together. So that's what we call side by side overlap. Okay. So as drawn, you might not see the side by side overlap, but in reality, it looks something like this. So you see this side by side overlap. That's so these two things are what we call pi bond. So it's not interacting directly with the two atoms' nuclei. It's interacting on this side by side overlap of the p orbitals. Okay, so that's a pi bond. All right. Okay. So resonance is still confusing. That's pretty much how resonance works. So this could work with also lone pairs of electrons, and that's because this lone pair here, one of the lone pairs is in a p orbital. That's why you go for a double bond there. Okay, so for radical halogenation, it proceeds most quickly with radical halogenation. All right, is fastest for fluorine, so for F2, okay? So it's fastest for fluorine, it's the slowest for bromine, and does not occur for iodine because iodine is overall endodermic. Okay? And this is, the reason here is, so fluorine has the smallest, most electronegative atom. Okay, so it reacts the fastest. So when you have the smallest atom, the electrons are going to be held more tightly, and so it will want to react with something to steal some of these electrons. So it'll form a strong polar bond. So it reacts the fastest. Bromine is the slowest because it's the largest atom. Okay. And electrons are most stable in this case. So when we form a bromine radical, right, we're comparing a bromine radical and a fluorine radical. Okay. So fluorine, the radical, so what happens is the radical here, it's closest to the nucleus of the fluorine atom. So now it doesn't have an octet. And so since fluorine is so electronegative, it will want to bond with anything that it can take an electron from. So that electron is the most reactive. So we could say electron in fluorine is most reactive. And that's because the electron in fluorine is most reactive because it can it can, what's the best way to put this? So the fluorine, it's most reactive because if we think about a fluorine atom, it has the highest electron affinity. Or, the highest electron affinity. So what that means is that it releases energy when forming an ion. So that's one way to look at it. Bromine, on the other hand, is least reactive. And that's because it has a lower electron affinity. So it doesn't have an affinity for electrons, and that means it releases less energy or takes energy to add an electron. So it's an unfavorable process. So that's why fluorine reacts with everything, pretty much everything. And so here's fluorine radical versus bromine radical. So I guess 2 trends you want to keep in mind. You probably want to keep in mind of all the trends you learned in general chemistry: ionization energy, electron affinity, electronegativity, and atomic size. They like the properties you learned there, you can apply them for these trends we teach you in OChem. So I would keep those in mind, or don't completely forget about them. Okay, so let's now talk about some acid-base stuff. Okay, so I'm not sure if you learned about this, but so acid and bases, remember so I guess the 2 terms here is you have either an acid that donates a proton in solution, like HCl, and then a base will react and generate OH minus, or take a proton and form a conjugate base here in solution. Okay. Now this is the Bronsted-Lowry definition. Now let's talk about the Lewis definition. So the Lewis definition is something like this. So HCl, it will donate a pair of electrons. No, wait. Let me see here. All right. So Lewis. No. Okay. So it's kind of the opposite. So let's do H2O again. So in this case, you have electron pairs. So what's happening is that the water is taking a proton here, and the bond is going to break to go to chlorine to give you Cl minus plus H3O plus. So in this case, a Lewis acid, okay? Lewis acid accepts a pair of electrons, so electron pair, into an empty orbital. In this case, the empty orbital is H plus. Okay? So you see how the H now, so all the electrons in this HCl is on the chlorine atom because it's polarized, right? So it's partially empty. So what happens is the water donates electrons into the empty H orbital, and it forms a new bond. And so we call Lewis acid a electron pair acceptor, and the electron pair donor is the Lewis base. But if you haven't come across this, I wouldn't worry too much about it. Okay? So we can actually predict acid base strength based on the stability of the acid base, conjugate acid base pair. Okay. Okie dokie. All right. Okay, so remember in okay, so I think that's enough of that. So now okay, okay. Okay, so the last thing we'll talk about is stability of radicals. I mean, the last thing we'll probably talk about in terms of vocabulary is stability of radicals. Okay, so so stability of radicals is based on hyperconjugation. So hyperconjugation is the interaction of a radical with a bonding orbital that's nearby. Okay, so we call it the overlap of neighboring orbitals. That stabilizes radicals. So you may have heard this. So this will make tertiary radicals the most stable. Tertiary radicals, the most stable. Stable alkyl radical. And this makes methyl radical, which has no stability. Methyl radical, the least stable. That's why it's really hard to form anything that could come from a methyl radical. Okay. All right. So example of this is, say you have this group right here. Okay. So here's my radical. Well, let's make it a little bit different. So here's the this is a tertiary radical, right? So the radicals and positive charges, they exist in what we call, let me try drawing 3D shape here. So here's my radical, right? It exists in a p orbital, all right? So what happens is that neighboring radicals, neighboring orbitals, so electronic orbitals on adjacent carbon atoms like this. Don't worry, you don't have to draw this, but I'm just drawing this to illustrate something. So basically, these orbitals can interact with each other, and they kind of allow delocalization. They allow, what I should say is that they allow electron density to be shared between the radical, which is unpaired. So when you have more electron density around a radical, it's more stable. So that's why there's several interactions here that can stabilize this radical. Okay, so that's called hyperconjugation. It's like resonance when you delocalize the charge from like a positive or negative charge. But in this case, you can't really draw resonance structures with this molecule. So this is how some radicals are stabilized even though there's no resonance structures. So this is what we call induction. So so you see carbon groups, so methyl groups or alkyl groups, they tend to have a lot of electron density that can be shared. So that's hyperconjugation. So that explains why tertiary radicals are the most stable. And that's why bromine, when it reacts with in halogenation reactions, the radical is not very reactive, so it tends to pick the radical that's the most stable because that will be generated the fastest in a chemical reaction. If you have the possibility of having different substitution products, primary at the primary position, secondary position, tertiary position. So in those cases, it is usually what we call a late transition state. So the reaction goes based on the formation of the radical pretty much first, rather than having the halogen kind of reacting quicker than the radical forming, if that makes sense. But if that doesn't make sense, don't worry too much about that. It's not particularly important for what you have to know. But it'll just make a lot more sense if you think it that way. But it's okay. All right, so that's kind of like the vocabulary I wanted to go over. Everything else, we should be okay with. Okay, so one thing I want to mention is also some rules for resonance. The last thing we'll go over some rules for resonance, in case students are still confused about that. So, in resonance, right, we can sometimes move lone pairs. Okay? I'll give you an example. Here is benzene, and here is its nitrogen derivative, pyridine. So nitrogen has a lone pair, but okay, this is probably a bad example to use. Okay, let's use a different one. Let's talk about furan. This molecule. Okay, so this oxygen has a lone pair that can move and generate resonance structures. Okay. Like that. Okay? Now, pyridine, however, can't do this because if you did this, right? So let's say you try to move pyridine's lone pair here. Well, we can't do that because there's already H here, and that will be an octet. So that will be carbon with 5 bonds. So no way we can do that, okay? So now let's go back here. So see, lone pairs sometimes can be moved or not. And then, we can't do this. So let's say we do this. Boom, 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 boom. Okay? If we do that, we get a structure like this. So it looks fine right now. Okay? Okay. So, I mean, this is essentially the same thing as doing this, right? We can also just do this. So that's like doing this thing. Okay, whoops. It's just like doing this, right? Bam, bam, bam. Okay? And then we get this first structure. Okay? So we have the lone pair. So the reason why we don't do something like this, so that's fine to do. But now let's actually move the lone pair. So we can't do something like this. So this may look okay on paper, but you see there's something wrong with the nitrogen here. And you see here now the nitrogen. It looks like it's carbon dioxide, right? So this nitrogen has two groups of atoms around it, two double bonds, so it looks like CO2. But the thing is, with CO2, the bond angles are 180. And for nitrogen, it looks like it's a little bit less than 190. It looks like 120, right? These look like 120. Remember, with ring strain, if we constrain something that's 180 into 120, this is going to be very unstable. Very unstable. So this is virtually, so nearly, so we could say very unstable here, and so not going to be formed. So not formed, okay? So not formed, not resonance structure. And that's because these electrons here, these electrons that we originally drew for pyridine right here, they are localized in sp orbital, sp2 orbital. So for all these, in order for pyridine to do resonance, all the atoms are sp2 hybridized, sp2, sp2. Remember, it has to all be sp2 hybridized to do resonance, like I showed earlier up above. So if it's sp2 hybridized, this lone pair is in sp2 orbital. And remember, only electrons in p orbitals can move around in resonance. So that's why this lone pair is not going to be able to be moved to draw a resonance structure, just by these two criteria alone. Okay? All right. Okay. All right. So one can, so then in that case, so for in resonance, we can also, sometimes it's possible to move pi bonds. Okay? So one example is, so you can move pi bonds in this situation, right? Like say you have a carbocation here, you can move pi bonds like this to generate this structure, and then move right here to generate the other structure. Okay? However, you can't move pi bonds when it's completely isolated, like this. So there's no way to move pi bonds like this over here and then make this jump up, because that will form a new structure, right? So that will be something like this. And I'm pretty sure that structure is not very stable, so this is not a resonance structure. Okay, so not resonance structure. So sometimes it's possible to move pi bonds. So you only can move pi bonds if it's adjacent to a positive charge or another pi bond. Okay, so another single or double bond. So pretty much another double bond in most cases. We rarely see triple bonds like this. So I want everyone to focus on double bonds. Okay. So it has to be adjacent. So the double bond or pi bond has to be adjacent to another to a positive charge. So right next to a positive charge, or another pi bond. Okay. And by there's two cases we should consider here. So you can't move pi bonds when they're when they're connected to the same atom. Okay, so say you have two pi bonds, right? You're not able to move pi bonds like this. Okay, so you can't move these pi bonds because you can't make a triple bond here, right? Because you'll be violating the octet rule, so you can't do this. You can only do this if the pi bond is next to only when it's next to the atom with the other pi bond. So see how this pi bond is next to the atom with the other pi bond, whereas these two pi bonds right here are connected to the same atom. So you can't do that. They have to be right next to each other, meaning that they should have some space between them, a single bond between them. Okay, so this one would be okay, because then you can move it like this. Okay, so that's resonance. Wow, can't believe that took an hour. Okay. All right. So this video is long, so just go through what you need. Maybe you don't need to watch most of it. So, but for students who want a crash course on the topics, by all means, watch this before your exam. And I think you should be in a better place than maybe if you're kind of struggling, you feel kind of nervous. Maybe watch this video, maybe help you. Okay, now let's go over some examples, more in-depth examples. Okay. Well, sorry, 3 p.m. Okay, nomenclature. So let's do a few nomenclature problems. All right, so let's okay, let's name this compound. Okay, so let's name this compound. So we want to number with the most substituents. So it looks like let's number it this way. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's 9. So that's 9, and we have 1, 2, 3 substituents in this path. Now let's use a different color and number it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you see we get the same number chain no matter if we start from the branch sticking out to the right or the branch sticking a little below that branch. Okay, but this one in black has 1, 2, 3, 4 substituents. So this has 4 substituents. So we're going to now use the route in black because that has the most substituents. So we have 2-methyl, 3-ethyl, 6-chloro, and 7-bromo. Okay? So we're going to put that all together. So alphabet comes first, 7-bromo. Oh, wait, and so the parent chain is nonane. So it's 9 carbons, right? So nonane. 7-bromo, 6-chloro, 3-ethyl, 2-methyl, nonane. Okay, so that's what we do. All right, so that's the one so that's a pretty straightforward example. We used No, we didn't have to use any complex substituents. But now let's use, now let's do another one where the substituents are now a little more complicated. All right. So let's do a cyclic example. Okay. Bam, 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 bam. Okay. So we have now stereochemistry to consider. The bonds has one dashed, one hash bond. So this is going to be a trans isomer. So now we have, okay, which one gets the, how do we number this carbon? So we know it's a cyclohexane. So what gets the substituent here? What gets the first position? Well, we have an isopropyl, or we can also call this 1,2,1-methyl ethyl. So we call it 1-methyl ethyl. This is isobutyl. But we can also call this 1, 2, 3. We can also call this 2-methyl propyl. Okay. So we could do an iso. So depending on which one you use, the common name for the substituent or the complex name, you have to be consistent. So if you're not consistent, the name will be wrong just by default. So make sure you're consistent in which naming you want to use. But you have trouble remembering isobutyl, isopropyl, just name it the systematic way. That's also fine. Okay. So if we compare these now, we have 1-methyl propyl and then 1-methyl ethyl. So, yeah. Okay, so it really depends on how you number it. So yeah, it depends on what name you use. So that's okay. So if we use the isopropyl, isobutyl, iso doesn't count in the name. Well, iso does, I believe. But butyl comes before propyl, so it'll be 1, 2, 3. So it'll be trans 1 isobutyl 3 isopropyl cyclohexane. Okay, but now if we use the other nomenclature, 1-methyl ethyl versus 2-methyl propyl, well, methyl and methyl is the same, but ethyl comes before propyl, so we will number it this way: 1, 2, 3. So then it'll become, if we're using the complex and systematic names, it'll become trans dash 1 dash 1 methyl dash methyl ethyl. Okay. Dash 3 dash 2 methyl propyl. I don't have room. Let's just move it a little bit over here. Cyclohexane. Okay. So no matter what, just be consistent in what and how you're going to name it, and then you'll be good. Okay. So to wrap up nomenclature, let's just do an example where we draw a compound. So let's draw the following. We're going to draw 1 chloro. Oops. 1 chloro, 2 methyl, 5 dash 1 methyl propyl. Propyl decane. All right, so the easiest thing to do first is just draw the parent chain. So let's draw the parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10. All right. Now let's label the easiest substituents. 1 chloro, we can just say, okay, we have 1 chloro here. So here's chlorine. All right, 2 methyl. All right, so here's 2 methyl. Here's CH3. Okay, now at the 5th position, oops, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I have 11. Oh man, that ruined things. Okay, let's go back. All right, let's do this again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there we go. So chlorine comes over here, 2 methyl at the 2 position, and at the 5 position we have 1 methyl propyl. So 1 methyl propyl is, say here's my connection point. I'll have 1, 2, 3, 1, 2, 3, and it's going to be at the 1 position. So here's a methyl group. So we're going to attach it like this. Okay. So at the 5 position, 1, 2, 3, 4, 5, we're going to draw just what we drew out earlier. And there you go. That's my answer. All right, so now let's pretend we're going to say we have the same equation here. Can I copy it? Yes. You're brilliant. Oops, don't want to do that. Oops. Oh, technical difficulties. No. No, don't want to do that. No, stop. Stop it. Okay, we can move it. Good. All right, so instead of methyl propyl, let's do 1 chloropropyl. Okay, so how would that change? Well, you know, you'll have the same structure pretty much, right? Cl, methyl there. Boom, boom. 1, 2, 3, 4, 5. So here's the propyl group we drew earlier. Okay. But instead of a methyl at the propyl group in our complex or branch substituent, we're going to just draw another chlorine there. Okay? So it doesn't matter if it's chloropropyl, bromopropyl, iodopropyl, fluoropropyl, you're just going to replace the methyl group with a chlorine atom. So nothing too different there, right? Okay. All right, so don't worry, you don't need to know about functional groups. You don't need to identify functional groups, so don't worry about that. Okay. Okie dokie. All right. So, okie dokie. What else should we go over? So that's enough nomenclature, I think. All right. So, so we probably should go some acids and bases. Okay. 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 So, which is the most basic. So I'll show you some compounds here. I have ethanol. I have CH3O minus. CH3 minus on the carbon atom. OH. Well, I just drew that. Why did I draw that again? OH minus. And then, and let's say we have ammonia. Okay. So remember, the most basic compound is going to be the one that is, let's see here. So remember, the most basic compound, right, is the one that has the negative charge. So look for negative charge. Okay? So if they're all negative, then you'll have to compare each of them side by side. Okay? But just imagine these are we could actually would it be okay to do that? Okay. Maybe we should do that instead, because that'll probably be a more representative. Okay. Okay. So let's do something like this. Okay. All right. So all these have negative charges, right? So the next thing you want to think about is resonance. Negative charge is shared between atoms. So when you have resonance like this will decrease basicity because you're sharing the charge. And so it's going to be less localized to act as a base. So decreases basicity. Okay? So when the charge is being shared, it's less likely going to act as a base, and it'll be weaker. So acetate has resonance. So here's resonance. So those are out. So those are typically weaker bases because the negative charge is not localized. So this one has an oxygen and this one has an carbon. So if we were to compare the two, oxygen is more electronegative, so it'll hog the electrons more. So this has also electronegativity. So this will be also the weaker. It'll be a weaker base than say this group over here that has a double bonded O and also a carbon atom. That's also going to be weak. That's going to be weaker than this carbon atom because carbon atoms are the best bases. So one thing to also look for is electronegativity. Least electronegative atom is more basic because share electrons easier. Share electrons more easily. Okay? So atoms like fluorine or oxygen, they're weaker bases because they like to hog the electrons. So they don't like to share electrons with anything else. So pretty much anything with carbon with a negative charge or nitrogen with a negative charge, they're primarily the strongest bases we see in organic. Okay? So in this case, this one's out of the picture. This one's out of the picture. Okay, now our competition is nitrogen, NH2 minus, OH minus, CH3 minus. And then the criteria here is electronegativity. And in this case, carbon will win right here. So this is the strongest base out of all those three. All right, how about most acidic? Let's try most acidic. Most acidic proton. Now, it may be helpful to rank these two. Let me rank them really quick. Okay. So So the weakest one is acetate because it has an oxygen minus with resonance. So it'll be like that. And then the other one, this is called deprotonated acetone. So it's a conjugate base of acetone. So that one will be the, actually, it might be not be the best. Yeah, this might not be the best way to go about this. Okay. All right, so let's not rank base strength. Let's see here. Yeah, these ones, it's a little trickier. Okay. You know what, everyone? Let's erase this one. It's just because it's a little bit complicated. Let's make this one a little bit different. Okay. It's a little bit let's pretend it's this position here. Okay. This one, okay? So, okay, so even though, okay, so we have to kind of step back here. So even though acids, so the first one's acetate, right? Even though it has only one carbonyl group, it's the most acidic because in both resonance structures the negative charge is on the oxygen, whereas in this structure on the left here the negative charge is on carbon atom. So that's why this is why this one is a weaker base. Okay, so that would be a weaker base because the electrons being shared less. Okay. And then what comes next is OH minus, because remember the most electronegative atom is going to be least basic than the less electronegative atom. Then nitrogen minus, and then lastly is CH3 minus. So the ranking is 1, 2, 3, 4, 5. So this will be the ranking of the base strengths here. Okay. So the more resonance you have, the more, well, I wouldn't say the more resonance. So the more likely you're able to put the charge on electronegative atoms, and if you can share those electrons with more atoms, the less basic you are. But it also depends on what kind of atoms you put nearby it. So acetate's the strongest because the negative charge here can go on both oxygen atoms, whereas in structure 4 the negative charge also goes on the carbon atom, and that's just enough to drive up the acidity or drive up the basicity of the compound. And also, if we think about it, right, the negative charge is on the carbon atom here, whereas it's on the oxygen atom. So by default, carbon is more basic because it's less electronegative. So that's why it's a better base than the oxygen one. But the fact that it has resonance makes it a weaker base than hydroxide. Okay, now let's talk about most acidic proton. Boom, 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 boom. All right. So the most acidic proton is a situation where we compare so usually we compare some acids here. So let's compare a few of them. So let's just do one trend. And maybe let's do a few trends here. So let's think about ethanol versus HI. Okay, so which one's the most acidic? So this one has, if we draw their conjugate bases, right, we get OH minus, the minus OH minus, O minus here, and then here we get I minus. And then it donates. Then we have proton in solution, right? So that's the definition of an acid. Now we need to evaluate the base strength. So the stronger the base form, the weaker the acid is. So we want to look for a pretty weak base. So you see here, oxygen is a pretty strong base because it has a negative charge, and oxygen is a small atom, so that makes it a good base. So small atom, better base. And if it's a better base, this means weaker acid. So when it's protonated, it's a weaker acid, and that's just kind of the relationship between a molecule that acts as a base and acid. If it's a weak acid, and when it's deprotonated, it's a better base. Now I minus is a large atom, so that means better acid. It'll form as a better when it's an acid, it's a better acid. Okay. And that would mean it's a weaker base. So I minus, let's just say the acid form, better acid form, okay? Weaker base. So if we compared I minus to O minus, we will see that, when we treat acid spills, you never throw in sodium iodide, and that's because it's not a base. And the reason that it's a larger atoms, they can stabilize the electron better. So the electron, we can think about is that the electron, it doesn't want to. What's a good way to put this? So if you have a larger atom, the electron's more stable because it's stabilized by the large size of the atom. So if you think about I can't think of a good example off my head, but iodide is a weak base, and that's because iodine is electronegative. So I think if you just think of it in terms of electronegativity, the more electronegative something is, the more it wants to attract other atoms to itself to form a chemical bond, because it wants to, give up those electrons, right? It wants to attract other electrons to itself to form a chemical bond. So I'll try to attract, so in the terms of acids, we think of okay, oxygen's more electronegative. Well, it's kind of complicated. Remember, there's an electronegativity trend, and then there's also a size trend. So for the size trend, the size trend is that it's easier to form I minus and H plus is because this bond here is a weak. So this H bond is a weak HI bond. So that means easier to break. So it's easier to break, it forms a stronger acid in solution. This OH bond here, so we have the OH bond, more polar, harder to break. And that's why it's a weaker acid. Okay? So the weaker the bond, the easier it is to form ions in solution. And the more stronger the bond or more polar, it's harder to form ions in solution. So that might sound counterintuitive based on polarity, but remember, when things dissolve in solution, chemical bonds aren't breaking. And when we're forming acids, what's more acidic, you have to consider the OH bond breaking. So in this case, OH bond is more polar, harder to break, so it's not going to be as acidic as the weaker bond due to the larger size of the iodine atom. Okay, so that's the size argument. So this is the size comparison. Now let's talk about a few more. Now let's take the same alcohol and compare it to NH2. Okay, so we draw their conjugate bases now. Okay. So we look at these conjugate bases, right? This one has a more stable base, more stable conjugate base. And that's because oxygen is more electronegative. More electronegative. Okay? Less stable. Because nitrogen is a better base. So when you have a better or stronger base, it's less likely going to deprotonate because bases are reactive, right? They want to take protons away. So the more basic you are, the less stable you are. So the less likely you're going to form naturally. And you have to form this compound using a stronger base than was being formed, okay? So this is the trend in electronegativity. Okay? So there's electronegativity, there's resonance, and then there's size. Now let's talk about so another thing you could consider for electronegativity is this molecule. We have something like this versus this. These have more electronegative atoms, 4 in here, so this is going to be this ion is going to be much more stable than this because the 4 in atoms. So this one has no electronegative atoms nearby, near charge. Okay, whereas this one has very electronegative atoms. Near charge, near negative charge. So it's going to be more stable. So negative charge is very reactive, right? So it's stabilized if you have something that can attract electron density away from the oxygen. And that makes it less stable because it'll become less negative in charge. Okay? So the electrons from the electronegativity of the 4 atoms, it helps stabilizes the oxygen atom. Okay. All right. So you could kind of use that trend to predict acidity too. And then the one last one is, let's say we have this compound here versus this compound. Okay. So the base here is O minus. The base here is an acetate or a carboxylic acetyl bond O minus. This one has resonance. This one has no resonance. So in comparison to resonance, this one will be stabilized by sharing charge with other oxygen atom. This one, however, has no resonance, so it's not stabilized. So not stabilized at all in any case. The only stability it has is the charge being on the oxygen atom. But this one on the right has both the charge and resonance, so this one would win by default. So this is going to be more acidic. In this case, this is more acidic here. And in this case, this one's more acidic. And in this case right here, HI is more acidic. Okay, so that's acid and bases. So you could rationalize the acidity of any proton being considered based on these trends here: resonance, electronegativity, and size of the atom. The conjugate base, the size of the atom bearing the charge in the conjugate base. Okay. All right. So. let's see here. What else should we go over? So we should also know hybridization also. So don't forget about hybridization. And don't forget about the bonds. So let's just go over a few in this example. Say I have this very complicated natural product here. Boop, 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 boop. Do, 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 do. All right. Well, not done yet. Forgot something. Okay. So don't worry about what this compound is. It's a very complicated natural product. You can't actually. It's actually. I don't think. I'm actually not sure this product is, but it's a very complicated natural product. Okay. So let's just go around and assign some hybridizations here. All right. So let's go to this carbon atom. So this will be an alkene. So it's sp2, right? Because it has a double bond. So pretty much any double bond, a neutral double bond, it'll always be sp2. Okay, it'll never be sp3 or sp. Well, it depends also. So you have a double bond, and it's only connected. It has 3 groups around it. sp2. So this one has an H, the other carbon atom, and the double bond. So that's 3 groups. sp2. All right. Now, if we take a look at this bond here, so the double bond, what orbitals are being formed? What orbitals form that bond? So we have 2 carbon atoms, right? They're both sp2 hybridized, so we're going to say C-sp2 and then C-sp2. Okay? So you don't just have to label it. Don't have to draw anything. Okay? All right. So if we look here, oxygen B here. So according to what you have learned in lecture, we're going to say it is not going to be hybridized, right? Okay. Okie dokie. Yeah. So this one we would say not hybridized in this case. Okay. So B. Okay. All right. As well as chlorine, unhybridized as well. Okay. All right. Now, let's see here. Okay. So we did those. Alrighty, so how about this atom right here? This one would be sp3, right? Because it's a tetrahedral carbon. sp3. And then how about this one right here? This double bonded alkynyl carbon, that will be sp because there's only 2 groups around the carbon atom. A triple bond and then the methyl group. And so if we were to point to this triple bond, okay, so the orbitals there would form as a CSP to a CSP, okay, like that. All right, now if we point to this bond right here, all right, so that's going to be a CSP3, right, and then the nitrogen there, oh, see the nitrogen, it's in resonance with this double bond here. So this nitrogen is actually going to be sp2. So we're going to say nitrogen is sp2 here. Like that. Okay? So yeah, you kind of do things like that. Okay. So now let's say, So let's say, okay, so now let's say we have a structure. Let's kind of now let's write the shapes of each of these atoms. So if we were to look at the shape of this carbonyl carbon right here, this carbonyl carbon, what shape would that be? So this one would have a trigonal planar shape, right? Trigonal planar. Now, how about this alkene? What shape would this have? Well, it's an alkene, sorry, not alkene, alkyne. So it's sp hybridized, so it's going to be linear. Okay? And lastly, if we looked at this oxygen atom here, since it has 4 groups around it, it's going to be tetrahedral. Okay, so that's pretty much all the geometry you can draw. Okie dokes. Oh, okay, but it's oxygen, right? So it'll probably look bent too, or bent. You could say tetrahedral, but bent is also okay. Bent is probably better here. But tetrahedral will work fine. Okay. Okay, so I went over resonance. So get some practice with that. But if people need practice, we could do this structure. Okay, so I will draw one additional resonance structure. Other students can draw some more. So here we go. All right. So if we move the resonance structure like this, oh wait, I forgot positive charge here. Like that. Okay, so there's 2 more resonance structures we could draw. Okay. So there's one there, and then there's another one. Let's draw a box here. And there's another one. Okay. All right. But for simplicity, let's just draw it here. You can do this as well. Then you have a negative charge here. Okay. And then lastly, you can draw the negatives. You can draw the charge back here and push the electrons back onto the nitrogen, and you get this structure. So in this case, what is the major resonance structure? Well, all these structures have separation of charge except for the last one. So this is the major contributor. So major structure. And this is because no formal charges. Okay, so that's our major structure there. Alrighty, so yeah, this is a pretty long video. It's almost 2 hours. So last thing I'll go over is a few, a few stability problems. Okay, so let's make sure we also know how to go from condensed structures to bond line, or so say we have these 2 structures here. So say we have this structure. CH2, CH3, CCH, CH, CH24. Oh, I guess it's okay to write condensed structure like this. It's fine. There's no issue with that, I guess. But, if you have multiple atoms at the terminal end on the same carbon atom, don't put them in parentheses. So we took points off for that on the quiz. So we have 3 alpha groups, right? So let's draw 3 alpha groups. And they're now combined to 1 carbon atom. So that carbon atom should have no hydrogens. And then it looks like we have an alkene here because it's CH-CH. And that's usually when you have an internal alkene because it's connected to 2 carbon atom. And there's a double bond. So the only other atom that could be connected to it, if it's not written, is hydrogen. CH-CH. And then we have 4 CH2s. 1, 2, 3, 4. So draw pretty much 4 CH2 groups. 1, 2, 3, 4. So, and pretty much you're going to draw 4 angles. Okay? 1, 2, 3, 4. And then lastly, it's going to be CN at the very end. Okay? Yeah. There we go. Okay, so that's what we would expect here. So you could draw it as CN, or you can do it as CN is also equal to this C triple bond N. But if you don't know that, it's okay. All right. Lastly, let's talk about stability questions. Okay. Okay, so chair cyclohexane. So which is more stable? As written, okay? Cyclohexane versus the chair. Okay, so in this case, this is planar cyclohexane. This is the chair form of cyclohexane. So if you just remember the insignia on a Heineken bottle, or no, it's not Heineken, but Bud Light, it's basically a chair. So if you can remember that symbol, you can probably draw a chair. All right, so chair versus planar. So in this case, the chair is more stable because the chair form avoids the torsional interactions in the planar form. Okay. All right, how about this? The eclipse form or staggered? Staggered, right? Staggered is more stable. All right, how about this structure here, 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 here. Boop, 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 boop. Do, 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 do. Boom, 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 boom. Okie dokie. Okay, so this one might look a little confusing, but if we think about it, in this case, on the left we have two anti configurations. So we have two methyl groups, and the other two methyl groups are in anti positions. But when we do that, we have a lot more gauche, I think, no, we have less gauche interactions when we put them like that, right? And then on the structure on the right, you see here the methyl groups. There's more gauche interactions, right? So there's more methyl groups closer to each of the other methyl groups. So in this case, this one would win. So we could say fewer gauche interactions. More anti, I guess. More anti. So you see, there's at least two anti groups here. Two of the pair of the methyl groups are anti to each other. Okay. So here's an example of an octet of resin structures. So which one's the more stable structure? It's going to be the one with all octets, no charges. Okie doke. So okay, so which is more stable? The cyclopropane with equivalent oxygen, or propane, just regular old propane? Well, remember that the linear versions of the cyclic versions are more stable because they have no ring strain, so we're going to circle the propane. So this will be this is an exothermic reaction. And that's why the propane is more stable. Okay? All right. All right. So how about this? Another resin structure here. Okay, so which one's more stable? Well, they all have octets, so we have to look at where the negative charge is. So the negative charge on the electronegative atom will have the more stable structure. So here we have more electronegative atom with the negative charge. Okay, so the more electronegative atom has the more negative charge, so that will be most stable. Okay. How about we have a set of eclipse interactions here? Alrighty, so this is going to be a set of eclipsing interactions here. But one of these groups that's going to be eclipsing, or you're going to have at least one of the groups be methyl. Okay. So what's the difference here then? So we still have eclipsing interactions, but now we're going to have two methyl groups trying to pass each other. Okay. So in this case, the larger groups are further from each other, so that's going to be this structure here. So in this case, we have no large groups passing each other. So when no large groups are passing each other, it's going to be more stable because there's less unfavorable interactions in this case. Okay, so how about this one? which was more stable here? Well, remember in substituents, in the axial version, we have 1,3 diaxial strains here. So it's going to be equatorial. Where, so it's pretty much, these interactions happen when they're at an axial position and they're across the ring. So equatorial will always be more stable. So large group, equatorial. So that's our criteria here. So that's the more stable group. Okay. And now let's go on to some acid-base stuff. So here we have deprotonated ethanol versus deprotonated acetic acid. So which one's the stronger, and which one's the stronger acid? So the more stable base or weaker base. So it'll be, we kind of talked about this before, so it's going to be this one because of resonance. All right, so which is more stable? Methane versus reacting with fluorine radical, or fluorine atom, or methyl radical reacting with HF. So remember, radical stability. So usually, the smaller the atom you have, the more reactive it is. So we know this reaction is exodermic, right? You learned that in class. So this is CH4 plus F radical. That's not very reactive. That's very reactive, sorry. So the more stable compound is this, because we know this from lecture. This is an exodermic reaction. So that means the left side of the reaction is very unstable. And you can kind of think of it as that F is smaller and more electronegative than CH3 radical. So radicals are considered electron deficient because they don't have an octet. So the more electronegative you are, the more unstable you're going to be because you're decreasing electron density from that radical electron. Well, I guess electronegativity won't be a good analogy here. So what we should say is F is smaller and has more has higher nuclear charge. Okay. So when it has a higher nuclear charge, right, it's going to pull on those electrons more tightly for the radical, and that will make it more reactive because you're essentially making you're decreasing. Well, I wouldn't say decreasing, but you're it's kind of hard to imagine. It's kind of hard to explain why the F radical is more reactive than the carbon radical, and I think it has to do with fluorine. Fluorine is smaller than carbon, so usually smaller reactive. So things with less than 8 electrons, they're not very happy. So the smaller the atom is, the the more reactive it is. If we think about small molecules like oxygen, hydrogen, very reactive, and that's because they're very small molecules. And so fluorine is more reactive because it kind of doesn't have anything to stabilize the radical. So whereas carbon, methyl radical doesn't also have anything to share its electron, but it's less electronegative than fluorine, or it has a less nuclear charge, a lower nuclear charge than fluorine, so it's not going to be destabilized by the nucleus. But if you just think about, oh, this is a very exothermic reaction, and that's because fluorine will want to react with many things, whereas carbon, it's more selective. So carbon-based radicals, they're usually more selective, and they would want to react in such a way that you produce a weaker radical, like bromine or chlorine. Or, or combine with another radical so they don't react. Okay? So in this case, F radical is smaller and has higher nuclear charge than methyl radical, so it's less stable. Okay. All right. Few more dings here. So we have H plus Br minus versus H plus F minus. Boop, boop, boop. Okay, so which one's the stronger acid? Well, remember, in this case, bromine and fluorine are of different sizes. So you could think about which argument to use, whether or not the atoms with the negative charge, are they from the same period or are they from the same group? If they're from the same group, we're going to look at the size argument. And bromine is higher than fluorine, and it's way more acidic than HF. And that's because it's a larger atom. Larger atom with the negative charge. Okay? All right, lastly, let's look at the methyl radical again. Versus a similar radical versus the isopropyl radical. So remember, radical stability is based on how many carbon atoms are attached to it. So when you have carbon atoms, you have more electron density to share with the radical, so it's more stable. So in this case, the more substituted radical, the secondary radical, is more stable, so because of hyperconjugation. There we go. So that's for stability here. Okay. Okay, so one last thing we should go over is the radical halogenation, the mechanism at least. I'll at least go over that so people are not kind of lost on what to expect. Okay. Okay. All right. So first thing I want to go over is this structure here. Okay. So we've used chlorine. What are the possible products we can get? Okay. So if we think about the mechanism, you know, so in general, so remember, in these reactions, what we're doing is substituting a CH bond with a CX bond. So there's a few positions that we can substitute, right? We can substitute here. Here's an H. Okay, here's an H. Here's an H. Here's an H. And then that's it. Okay? Because these last two positions here, they're equivalent to the other side. If we assume if we assume that we only get monochlorination, okay? So usually that's what happens, because usually the halogen gets all used up before you can even do a second addition of a halogen. So it's usually monochlorination. So let's draw the following products. So let's say we substitute at the terminal end there. So we're going to get Cl okay, this product. So what would happen if a chlorine attacked a primary position on the linear chain? Okay, then we also can get a secondary position where it will bind to the secondary position towards the parent chain here. So that's if it attacked the H from the CH2 group. All right, you can also get substitution at the tertiary position. So there's only one tertiary position, and it's going to be this one. So you get a symmetrical product. And then lastly, it can attack the other primary position, which is this product here. The product coming off the branch in the parent chain. So you can get 4 possible products, right? So let's see here. Okay. Okay, so which one will be the major product though? Okay, so to calculate the major product, well, I'm not sure Dr. Nasiri went over this, so if she didn't, just ignore this. But if you went over the abundance, basically the abundance of the product is the number of H's times the ratio of selectivity. Okay, so in the first product, there's 6 positions, right? So there's two terminal methyl groups that are equivalent. So that's when we can say 6 times 1 equals 6. So the relative abundance of this product is like 6% or something. Well, I can't actually put a number on it, but we'll just say 6. Okay, for this product. So let's just number these. A, B, C, D. So here's A. All right, for product B now, we have 4 positions. So the number of H's is 4. And then the selectivity for secondary positions is 4. So the relative abundance is 16. Okay. Now let's go to the third product, letter C. So we have only one equivalent hydrogen times 5. And that gives us only 5. Now with D, we have 3 positions here. So 3, and as a primary times 1 equals 3. Okay. All right. So now, if we were to find the relative abundance, to find the relative percent of each product, we would combine these into percents. So for A, it will be 6 over so 6 plus 16 plus 5 plus 3. That would give us 30. Okay. B would be 16 over 30. C is 5 over 30. And then D is 3 over 30. Okay. So if we represent these as percents, we would get 6 over 30. That is 1/5. So this will be 20%. 16 over 30, that's over 50%. 5 over 30 is less than 20%. Then lastly, we get D, which is 10%. So that will be our abundance ratio there. See that? Okay, so the key things to take away is that, remember the ratio for chlorine is 1 to 4 to 5. So you have more secondary positions where we have that for B, you see that will be the major product. And that the rest of them will be like 10 to 20%. So that's not even half. That's pretty much less than half of what secondaries will get. So in a compound with lots of secondary positions, if you have more secondary positions than tertiary positions, coordination will always favor the secondary position. So coordination favors the secondary position. Secondary substitution. Okay? So that's how we would predict those products. Now, Masuri might not have went over this, so if she didn't, don't worry about it. But I got some questions about why in this compound, why does it prefer the secondary position rather than the tertiary? Aren't tertiary more stable? Well, in this case, it doesn't depend on the stability of the tertiary, of the radical of the alkyl, of the alkane. It actually depends on the selectivity or reactivity of the chlorine radical. So the chlorine radical in this case is fairly reactive, that it will trump the preference for radical stability. So don't always assume that the most stable radical will get substituted first. It also depends on your other reactant, which is the halogen, the gas, the halogen. So chlorine, bromine, or fluorine. And as you go from fluorine to bromine, the halogen radical gets less reactive, and that's why bromine prefers tertiary position. So you think of this way: fluorine, no selectivity; chlorine, secondary; bromine, tertiary. And you kind of recite that in your mind, you cannot go wrong. Okay? All right, so the last thing, so this is a long video, sorry. So the last thing I want to go over is, let's go over the mechanism. So for this reaction, let's just go over one reaction here. So let's say we're going from here to the major product here, which is undoubtedly this one. Okay, so let's write the mechanism. So write the mechanism. Okie dokie. All right, so let's write the mechanism. Oh, so that's a long notes. All right. So So say I want to form, so let's write all the radical steps, right? So how does this reaction occur? So this will be the last thing we go over. So the first thing is initiation, right? So we have to form our radical source. Man, I cannot spell today. Okay. So remember, the radical reactions, they always start where the weakest bond is broken first. And CC bonds and CH bonds, they're not particularly weak unless activated. And so by a metal or something. But so in this case, the weakest bond is the halogen. So we're going to break up the halogen bond. So CCl. Here you go. So that's initiation. So now we're going to write two propagation steps for the reaction now. So propagation is pretty much where you extend the chain of the reaction or the formation of the radical. So we're propagating the radical chain mechanism by forming another radical. So there's two reactions here. The chloride radical will react with our starting material. So in this case, we want to form the secondary position. So we're going to take the hydrogen from this position and react it with the radical. And then the electron will go back onto the carbon atom since it's homolytic cleavage. So we get that. So we get this will form HCl, so it binds with the hydrogen atom, and then it forms this radical here, right there. Okay. Now, then we have two possibilities. It can go to, we have the other propagation step, where the carbon radical now is going to bind with another chlorine atom, and thus, or reacts with a chlorine molecule, and then regenerates the chloride radical, so it can repeat the steps. So the radical chain mechanisms, they're like a cycle. So you form the radical reacts, regenerates the initial radical, and then the process begins all over again until you run out of chlorine, basically, or starting material. So it's like a self-containing reaction that acts in a cycle. So it's kind of like clockwork. You're kind of working on the cycle, and you kind of just work until the reaction stops. But heck, I may have gotten that idiom wrong. So apologies if I did. Okay. So, you have another chlorine radical here. Sorry, chlorine molecule. So this radical will react with the chlorine. And then you regenerate the you regenerate the radical and generate the final product here. Okay. All right, so that's the propagation step. So that's the propagation. There's two steps. The chlorine radical generates the alkyl radical, and then the alkyl radical will form the final product, the haloalkane. Sorry, someone's blaring their horn outside my house. So sorry if you heard that. Anyway, right. And then the alkyl radical will form the final product, and then you form the chloride radical. And so these reactions are synthetically useful, but that's only if you can if you can isolate one major product. So this one is okay, but as you see here, our yields are not very good. So we only get 50% of maybe the product that we want, the secondary position. And if we want the primary positions, this is not a good way to form the product. So in organic chemistry, it's I kind of like think of it like an art, like scientific art. You're kind of constructing your a molecule of of unimaginable complexity from very simple molecules you can find in nature or like in the chemical industry. So I think it's like if you're bad at actual art, you can be a chemical artist or a chemical architect and makes molecules that can basically, be have the potential to change industries, provide materials, medicines, polymers, new materials, new interesting, fabrics, materials. So polymers encompasses a lot of things: fabrics, plastics, materials you see every day that you don't really put a second thought into where they come from. Biorenewable substances, which we can replace dying industries, or industries that are not very sustainable anymore, or where the clock has run its course on certain processes, like fossil fuels, right? We can't expect fossil fuels to replenish itself because it takes millions of years to do that. And the reason why fossil fuels are around now is because of degrading animal matter, or basically, matter that has went back into the earth after degradation of eons or untold number of years. So the future of the world we live in is kind of on a steep cliff right now. We need to kind of think about new ways to approach chemistry, and new ways to think about what we're teaching you, and like what are better ways to do things. Not just using old chemical methods, but also using methods from biology, from geosciences. So it should be a collaborative effort. But that's why we have people in all the sciences, so they can all work together and somehow figure out a solution to our current social, economical, and political problems in the current age. Okay, but anyway, so that's the mechanism. All right. So you also want to be aware of the terminal. The last step there's initiation, propagation, then there's termination. So the termination of interest to us is when two alkyl radicals come together to form a side product. So in addition to all the products I've shown you, you can have two radicals combined like this, so plus radicals combined together, but these are very rare, but you do see it in the product distribution, so you would see this as a side product. So it would join here, like that, and it's kind of hard to draw, but if you kind of draw it upside down here, like this, and draw the other product upside down like a mirror image, so like this, then you draw the bond like there, then it'll kind of be easier to see. So you see how I kind of drew everything like a mirror image? That shows how the product can couple, and then you would just draw this. You can draw this, leave this like this, or draw it as a straight chain, which will be, in this case, so we have 1, 2, 4. Like that. Okay, so let's make sure we have all the carbons. 1, 2, 3, 4, 5, 6. 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And we have methyl positions at the 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is the side product. Okay, so that's that's the last thing I wanted to go over. So if you stuck around the whole video, kudos. You're very strong mentally. So good job. But this will be kind of like a crash course for the first midterm in case there are some students who need a little more direction in terms of what to know, what to expect on the first midterm. So I wish everyone luck. And my off starts on Tuesday, so I guess the Tuesday section won't be able to get help before then. But if you're on the Monday, Wednesday section, you probably can see me during my office hours if anyone has any last minute questions. And on Monday, I will be in my lab all day, so you can come catch me before I leave, which is like probably at 9 p.m. or something. Because I need to get some work done. So if you come by my office, Chemistry 349, you can find me there. I'll be in my office. I won't be in the lab. Probably won't be in the lab. But if I'm not there, just kind of wait for like a few minutes. I'll probably be back. But on Monday, I'll be in my office from at least from 10. I'll try to get in before 10, but usually I get in between 9 and 10, or sometimes before 9 at like 8:30. But I usually leave before around 8 or 9 p.m. So, but it'll probably be 9 p.m. I try to not leave after 10 p.m. because I tend to get a little droozy when I'm driving back to Sacramento. Okay, so that was the review. Any questions and concerns? If anyone wants me to post what I went over, I can do that. But that'll be it. Good luck. And like I said, for all exams, the worst thing to do is panic. I used to panic at my 8 a.m. OChem classes my sophomore year. So my recommendation is, if you're like me, I have anxiety, I have stress, I panic on exams, and I have tremors when I take exams. So when I was doing my exams, my hands would always shake, and I couldn't write clear, concise answers sometimes, or it took me a while to get through stuff because I would scribble on the page and my hand wouldn't listen to what I wanted to do because of my tremors. So, we all have those test anxieties, so don't worry too much. Try not to worry too much. And my recommendation is don't cram, don't pull an all-nighter, because you might miss the exam if you're on the Monday, Wednesday class because of that in the morning. And definitely don't put everything off to the last minute. If anything, the night before the exam, you should get a good night's sleep so you're well rested. Make sure you eat something before the exam so you have some energy, and then just do your best. Okay? So I'll see everyone during lecture for the exam. All right. Take care.